Thus far, we already worked a bit with our data in MongoDB, and we always work with it from inside the shell. That is also where we will stay in this course, since you're a developer and you'll write code, and we do write code in the shell. But from time to time, you might want to peek into your database in a graphical user interface. And MongoDB Compass is such a graphical user interface which you can use. In this module, I'll show you how to use MongoDB Compass, how to use it to insert data, to update and delete data, and of course, how to view it and get a feeling for your data. Of course, you cannot just use it to insert new data. You could also open a database server where you have a couple of databases with data in there already. That would work too. So let's dive into MongoDB Compass then. You can download MongoDB Compass from the Compass page on the MongoDB page. You can find it on Solutions, and there is simply Compass. Now on that page, you can simply click on Try It Now, and there Compass should be selected. Your operating system should be selected, otherwise you can change it here. And you simply download that, and you'll get an installer through which you can walk. And this should be pretty straightforward. Once this installation process finished, and I already installed it for me, you can start up Compass, and you should start on a page that looks something like this, where you can connect to a host. Now it's important that you have a MongoDB server up and running, and I do. I'm also connected to it in the shell, and you see, this is actually an empty server, no databases, no data. I cleared everything before this module by simply deleting everything in the DB folder where the data gets stored. You could, of course, also have some data in there, doesn't matter. And I got a MongoDB instance running. And that is the instance to which we'll connect. Now, the default settings actually already do suffice for connecting. We want to connect to localhost and to this port. So if you didn't change anything here, you can just click Connect. And you are connected to your local MongoDB server. Now you see the three default databases. Now here, we can actually create a new database. For example, we could add some contact data with the contacts collection and click Create Database. In the contact data, we now have the contacts collection, and as you see, we can even insert a document here. And there we could insert a name, Max, we could insert an age, 29, and we can change the type of that too. We could say that should be simply int 32, for example. We can then add another field, and that could be my location. And for location, I'll actually add an object, which is simply a nested and embedded document. And for the embedded document, I will add a special type of object, which I'll explain a bit deeper later in the geospatial module, where I'll set a type field to point. This is a string, point. And then I'll add coordinates. And coordinates will actually be an array. And here the first value will be a double, and that double, let's say, is 56.12. And then the second element also is a double, and that is, let's say, 43.09. Now let's click Insert here, and this was now inserted. Now you also see other tabs besides your documents. These are all things which will make more sense once we progress through the course. For example, the aggregation framework module will show you how you can aggregate data in the shell, but thereafter, this page will make more sense to you because what you'll learn in the shell later in that module is something you can also replicate in the user interface by then. Explain plan and indexes will make more sense after the indexes module, where you learn what indexes are and why we use them. And here you can explore which indexes are attached to your collection, which kind of index it is. You can also create a new index, and you can understand how your queries are executed. Speaking of queries, you can execute queries here too. Right now, I'm finding all documents, as you can see. Now you can also, on this page, of course, filter for different things. You can write a query, as you'll learn in this course, and as you already saw it a bit. You could, for example, search for age being able to 29. And of course, you would find that same document. If I searched for age 30, though, I'll not find anything. So you can play around with it and explore your data here a bit to get a feeling for what's inside. And of course, you can not just insert data and view data, you can also edit and change it. For example, here I could update Max to be 30 years old. Simply click update here and you're good to go. And if you want to get rid of a user suddenly, you can of course also delete this user. and click delete. Now I'll not do that here, but it would be as easy as that. Now that location thing here, that object, this is just showing you that you can add a nested object as well and an array. And this is actually a special type of object which you'll also learn more about in the geospatial module. So this is Compass, and this is a super short module obviously. Compass is a nice graphical user interface which you simply should be aware of. And even though I will not use it for the rest of this course, because this being a developer's course, I'll focus on the code, you can always come back and log into your database server with Compass to explore your data, to easily manipulate it, to try out some queries, and later in the indexes module, also explore indexes and explain tab, and in the aggregations module, play around with this graphical user interface. This is MongoDB Compass. Now there's one other thing to mention, and that is that this is the community edition. If you are using MongoDB Enterprise, MongoDB Compass will have one cool feature, and that is the schema tab, which we don't have here. This allows you to explore the schema of your data in greater detail. So you can see how many documents do have a string for name or a string for age, maybe if you have mixed data. For location data like this one, you would also see a map and you could explore your entries on that map for multiple documents. So with the enterprise version, you get a bit more features, but for basic exploration and editing, the community edition, which comes for free, should suffice. Now that you learned a lot about general queries and how to store data and how to retrieve data, it's time to also learn how to retrieve data efficiently. Now, we'll have a look at indexes in this module. And indexes are a feature that can drastically speed up your queries, though if used incorrectly, they can also slow down some of your operations. Now, we'll take a look at all of that and the different kinds of queries in this module. I just want to highlight that in general, you as a developer will most likely not create that many indexes. But if you're working as a single person on a web project, for example, and therefore are the single person using some MongoDB solution, you still will need to know how to create indexes. And even if you never create them, it's still worth understanding how indexes and queries work together. In this module, we'll have a look at what exactly an index is and how it can help us. We'll then have a look at the different types of indexes MongoDB supports, and we'll have a look at how you use indexes and how you can optimize your queries for indexes, or the other way around, how you can optimize your indexes to support your queries. So with that, let's dive in and let's learn how indexes can help us. So why would we use an index? And what is an index to begin with? An index can speed up our find, update, or delete queries. So all the queries where we are looking for certain documents that should match some criteria. Consider this find query. Here I'm looking for all products where the seller is Max. Now let's say this is my collection of documents, the products collection. Now by default, if I don't have an index on seller set, MongoDB will go ahead and do a so-called collection scan. Now that simply means that MongoDB, to fulfill this query, will go through the entire collection, look at every single document, and see if seller equals Max. And as you can imagine, for very large collections with thousands or millions of documents, this can take a while. And we'll see this in practice with an example in a second. So this is the default approach MongoDB takes, or the only approach it can take when you have no index set up, in order to retrieve maybe 2 documents out of your 1,000 documents. Now you can create an index though. An index is not a replacement for a collection, but an addition, you could say. So you would create an index for the seller key of the products collection here. And that index then exists additionally to the collection, and the index is essentially an ordered list of all the values that are placed or stored in the seller key for all the documents. So it's not an ordered list of the documents, just of the values for the field for which you created that index. And it's not just an ordered list of the values. Of course, every value, every item in the index has a pointer to the full document it belongs to. Now this allows MongoDB to do a so-called index scan to fulfill this query, which means it sees that for seller such an index exists, and it therefore simply goes to that seller index and can quickly jump to the right values, because there, unlike for the collection, it knows that the values are sorted by that key. So it doesn't have to look at the first 3 records if it's only looking for records starting with M, or to be precise, records equal to max. So it can very efficiently go through that index and then find the matching products. Because of that ordering and because of that pointer every element in this index has. So MongoDB finds the value for this query and then finds the related document and can return this. So it's this direct access that MongoDB can use here, and that speeds up your queries. So this is in the end how an index works, and it also answers the question why you would use one, because creating such indexes can drastically speed up your queries. However, you also shouldn't overdo it with the indexes, because you could of course think, well, okay, I got my products collection and every product has ID, name, age, and hobby. And then I could simply create indexes for all fields and I will have the best performance ever, right? Because no matter for what I look, I got an index for that. Well, this might speed up your find queries, that is correct. Indexes on all fields would speed up find queries because you can query for every field efficiently, but an index does not come for free. You will pay some performance cost on inserts, because that extra index that has to be maintained needs to be updated with every insert. Makes sense, right? Because we have an ordered list of elements with pointers to the documents. So if you add a new document, you also have to add a new element to the index. And that might sound simple and it won't take super long, but if you got 10 indexes for your documents in your collection and you have to update all 10 indexes for every insert, then you might quickly run into issues, because you'll have to do a lot of work for all these fields, for every insert and for every update too. Therefore, indexes don't come for free, and you really have to find out which indexes make sense and which indexes don't. And this is exactly what I will also do in this module with you. I will walk you through all the different index types that exist in MongoDB, and I will also show you how you can measure whether an index makes sense or does not make sense. So let's now have a look at this index thing in practice and understand the impact they have and how we can create indexes. For this, you should have a running MongoDB server. I have that in a second tab. And then you find a starting dataset attached to this video, the persons.json file. Download that file and store it somewhere on your machine, and then navigate in the terminal or command prompt into that folder where you have it stored so that you can easily import it with Mongo import. So simply type Mongo import, then the path to that file. And now since I'm running this in the folder where the file is, I can just type the file name. Then the database where you want to store this, and I'll simply create a new one, contact data, and the collection which you want to create for that data, and I'll name mine contacts. Now you also need to add JSON array at the end so that this gets imported correctly, and it should import 5,000 documents. Now if you connect to your database thereafter, you should have the new contact data database, which we can use now, so contact data, and in there you should have this contacts collection. So let's now use that contacts collection. And let's first of all have a look at a single contact. For this, I'll reach out to my contacts and find one element. So this is essentially what we have in there. This is some random person data. Each person has an ID, gender, a name, which is actually a nested document, as you can see, a location, which is a nested document, even coordinates here. We got a time zone, got an email, login data, date of birth, which is both the date and the current age, some registration date. Let's say this is for a web platform where people can manage their contacts, and each contact therefore also has the date when the contact signed up, and so on. So we get this basic dummy person data which we can use. So now let's run a query and let's find all people who are older than 60. So for this, I will clear my shell here. And I will then reach out to contacts, run a find method here, and I'm looking for the dob.age field, so for this field in the embedded document. And I'll have a greater than query, and the greater than query will be looking for people older than 60. Let's also pretty print this. And we get a bunch of results. 61 is the age here, 61 again. So there are some people who are older than 60, as it seems. We can also have a look at how many results we got by adding count at the end. So 1,222. Now, of course, this was a super fast query, but we also don't have that many documents in this collection. That's important to keep in mind. Now, in order to determine whether an index can help us or to see what MongoDB actually does, MongoDB gives us a nice tool that we can use to analyze how it executed the query. And this tool is a simple method we add to our query. Here, after you reach out to the collection, you can add the explain method and then chain your normal query. Explain works for find, update, delete, not for insert. So it basically works for the methods where you, narrow down documents, where you find documents. And then here we can, of course, repeat our condition, looking for DOB age to be greater than 60. Now here we get the detailed description of what MongoDB did and how it derived our results. MongoDB thinks in so-called plans, and plans are simply alternatives it considers for executing that query. In the end, it will find a winning plan, and I'll come back to how MongoDB determines this later. And that winning plan is essentially what it did to get our results. And you see here the winning plan was to do a full collection scan. We could also have rejected plans, but for this we would need alternatives, and without indexes, a full scan is always the only thing MongoDB can do, so there were no alternatives, and therefore the only approach we had, of course, is the winning plan. Now we can get even more detailed output by rerunning that command, but now we can pass an argument to explain. And that argument is a string where we control the verbosity of this command. If you pass execution stats here, and make sure you get that typed correctly with a capital S and a lowercase e, you find a detailed output for this query and how the results were returned. There, you see that the overall query took 5 milliseconds, which is of course super fast, but our collection is also not very big. And if it were bigger, if it had millions of documents, this number would of course scale up. And you see that we had to look at 5,000 documents in order to return our 1,222. So there's quite a big gap here. And this already is a sign that this is a kind of an inefficient query. Now let's add an index and see how this changes things. We do add an index to a collection by typing db contacts and then create index. Now an index is defined as a document here, and the first value, the key here, is the name of the field you want to create an index on. And in my case, that is dob.h. So you see you can create indexes on embedded fields just as you could use a normal field. So you can use top level fields, you can use embedded fields, doesn't matter. Then the value is whether MongoDB should create that list of values in that h field in an ascending or descending order. So it can sort by ascending or descending order. If you add a 1 here, it'll be ascending order, so lower values come first, higher values towards the end. If you add a -1 here, it's descending. What you choose here, in the end, doesn't matter too much. Even if you do sort your results and you sort in the opposite direction, it will still be sped up because MongoDB can traverse that index in both directions. So you can actually choose what you want here, and I'll go for ascending. Now this created an index. You see we had 1 before. We'll see which index that was in a second. Now we have 2. So with that, let's repeat our explain command here for people older than 60. And if we do that, we should see that now the execution time is down significantly from 5 to 3. So obviously we're talking about small numbers here, but the main thing is it was sped up. We also see that there are 2 execution stages now. And we also see that the first stage, the input stage, was an index scan. In the other output, that would be our winning plan essentially. So it did not do a full collection scan, but instead an index scan. And there you see that it returned 1,222 documents, or not documents to be precise, but keys in the index with their respective pointers at documents. So the index scan does not return the documents, but just the keys in the index and the pointers to the documents. It's the next stage, the fetch stage, which will then take these pointers returned from the index and reach out to the actual collection and then fetch the real documents from there. And therefore, in the end, we see here, we had to only look at 1,222 keys in our index to reach 1,222 documents which are returned. We also had to look at these documents because the index only has the pointer set, the documents, so the index just narrows down the set. We still have to go to the collection and get the documents from there to return them in the end. But this sped up our query, and this is how our index can help us. Now, before we dive deeper into the different types of indexes, let me also show you something interesting about this dataset, which helps you understand indexes a bit better. So we had a look at our first index, and this index actually sped up our query. It sped up our query for people older than 60. Now, something interesting happens if we do run the same query for people older than 20. If I do run this query, it's still super fast, but what we see is that we essentially seem to have no person in our dataset that is younger than 20. We'll have to go through the entire index, every single element matches our query, and then we fetch the documents for that. And you see that the execution time for this is higher than it was for people older than 60. Now, something interesting happens if we get rid of that index, which we can do by reaching out to our database, to our collection, and then running drop index. And now here we specify the exact same document we used for creating it. So DOBH and then 1. And now you see that index was removed. And now let's run the same query again, or explain it, now that we have no index. What you'll see is that this now actually is faster. We get an execution time of 6 milliseconds. Now, the reason why this is faster is that we save the step of going through the index. If you have a query that will return a large portion or the majority of your documents, an index can actually be slower because you then just have an extra step to go through your almost entire index list, and then you have to go to the collection and get all these documents. So you then just have an extra step. Because if you do a full collection scan, it can be faster, and it certainly is if you return all elements, but even for the majority it would often be faster, because with a full collection scan, you already have all the documents in memory. And then an index doesn't offer you anymore, because that just is an extra step. Instead, here we got all the documents in memory. We would have needed to go to the documents anyways to fetch them from the pointers the index gives us. So now we already have them, and since we need most of them, this is now faster. So if you have queries that regularly return the majority or all of your documents, an index will not really help you there. It might even slow down the execution. And that is important to keep in mind as a first restriction that you need to know when planning your queries. If you have a dataset where your queries typically only return fractions, like 10 or 20% or lower than that of the documents, then indexes will almost certainly always speed it up. If you get a lot of queries that give you back all the documents or close to all the documents, indexes can't do that much work for you. And logically, that makes sense, because the idea of the index is to quickly let you get to a narrow subset of your document list and not to the majority of that. Now we had a first look at indexes. Now let's again look at a single document in our contacts database. And we created an index for the age here. Now, we dropped it in the last lecture, but previously we did. Now, of course, you cannot just create indexes on fields that have a number. You can also create indexes on fields that have some text. And that makes a lot of sense because, well, text is also something you regularly search for, and it can also perfectly be sorted. Booleans, on the other hand, are something that don't make too much sense because since you only got two kinds of values, true or false, chances are that an index will not speed up your queries too much. Now, let's create a second index, or actually a first one because I dropped one. And let's now use a text index. And for that, I'll try creating an index on the gender, male here. I'll do this on my collection with create index. And I'll look for the gender field to be sorted ascendingly. Now, of course, one problem you might already think of is that for gender, just like for a Boolean, we typically only have two values. And indeed, if I do run an explain command with execution stats on my contacts, and I try to find all contacts where gender is equal to male, I should get back a lot of keys, right? I should get back like half the documents because this random collection of persons is pretty evenly distributed. And indeed, of my 5,000 documents, 2,400 are male. So this again is probably an example for an index that doesn't make too much sense or that doesn't really speed up our queries because we fetch the majority or a large chunk of our collection every time. Still, we use the index here, of course. This also tells us something about the winning plans and rejected plans, by the way. You see that MongoDB didn't seem to consider a collection scan because we have no rejected plans. So for the rejected plans, it also looks at other indexes, but not really at the collection scan as an alternative. So this index alone doesn't make too much sense. But there is another kind of index we can use. Because let's say we want to find all persons who are older than 30 and male, or older than 40 and male. And for this, we can create a so-called compound index. Now let me drop this index first of all, db contacts drop index, and I'll drop my gender ascending index here. And let's create a new one here. And this index will not just have the gender, but actually as a first key, let's say I want to look for DOB age, and that sort this in ascending order too. Now the order of these two fields here does matter, because a compound index simply is an index with more than one field. Like here, we got two fields. And this will essentially store one index where each entry in the index is now not a single value, but two combined values. So it does not create two indexes, that's important. It creates one index, but one index where every element is a, well, connected value. So now it will simply create pairs of ages and genders. So we'll have 30 male, 30 male, 30 female, 31 male, 31 female, and so on in the index list. And the order here defines which kind of pairs MongoDB creates. Does it create, let's say, 31 male field or a male 31 or 33 field? And this will be important for your queries, as you will see. So let's create that index. Created the index successfully. And now we can utilize such a compound index with two different queries. The obvious query that takes advantage of the index is that if I explain without execution steps here, a find query where I try to find all people where the age is, let's say, 35, and all the people who are males. So I can also set gender to male. So I got two elements in my filter here, the age and the gender, and these are the two elements I also have in my index. Here, the order does not matter, by the way. If I hit enter, you see it actually did an index scan with our index name, and this name is auto-generated. It indicates that this is a compound index because the name is generated from the values that are placed in the index. So this is a compound index, and this speeds up our queries for requests that are, well, going to these two fields because we have these two in an index. Another query that is sped up by that same index is if I just look for the age. If I do that, you see here, it also used an index scan, and it used that same compound index, even though I never specified the gender in this request here. But the compound index can be used from left to right, so to say. So if you have age and gender in there, and the leftmost value as you created the index was age, and then the second value was gender, then you can use this index either for all finds that look just for the age, so for the left part, or left and gender. Gender alone won't work though. So if I try to look for all males with gender male, you see that of course works, but it uses a collection scan and not an index scan because it can't look into that second value standalone. And that makes a lot of sense because if you got a couple of pairs of values in that index, 33 male, 33 male, 33 female, and so on, then you can obviously use that index if you just look for 33, because you just have to go through all the values because they are sorted by these key value pairs. And the first value, of course, defines the sorting for the overall index. So 33 comes before 34. the male and female parts are then also sorted, but only within their category. So only for 33, 34, 35. Of course, the male and female parts are not sorted on the overall list. Makes sense, right? Because they are grouped together with the age numbers. So therefore, you can utilize a compound index from left to right. So if you had a compound index with 3 or 4 elements, you can have up to 31. Then you could also just use the first 2, the first 3, or all 4, or just the first. But you can't use the fourth one or the third one. These are some restrictions you have on compound indexes, but compound indexes in general allow you to speed up queries that use multiple values if you create a compound index on these multiple values. Now that we had a look at the basics of indexes, it's also important to understand that indexes are not just there for finding, but they can also help you with sorting. Because we have a sorted list of elements in the index, right? MongoDB can utilize that in case you want to sort in the same way that index list is sorted. So in our example here, I could find, and I should explain this, of course. So I could find, let's say, all people with an age of 35, and then sort with that sort operator, and then sort for gender in an ascending order. If I execute this, you see that it did actually use an index scan for both gender and age, even though I only filtered by age, but it used the gender information for the sorting. Now, this is another cool feature of indexes. Since we have an ordered list of values already, MongoDB can utilize that to quickly give us back the order of documents we need. Now, also important to understand or to know here is that if you are not using indexes and you do a sort on a large amount of documents, you can actually time out because MongoDB has a threshold of 32 megabytes in memory for sorting. And if you have no index, MongoDB will essentially fetch all your documents into memory and do the sort there. And for large collections and large amounts of fetched documents, this can simply be too much to then sort. So sometimes you also need an index not just to speed up the query, which always makes sense, but also to be able to sort at all. Now, this is not the case for our small data set here, but if you have millions of documents, you could very well have a query where you fetch so many documents that an in-memory sort, which is the default then, is just not possible. And you need an index which is already sorted so that MongoDB doesn't have to sort in memory, but can just take the order you have in the index. So that's also something important to keep in mind, that when you're sorting documents and you have a lot of documents in a given query, you might need an index to be able to sort them at all, because MongoDB has this threshold of 32 megabytes, which it reserves in memory for the fetched documents and sorting them. Now you might remember that earlier when we created an index, it seemed like there already was an index. Now we can always see all indexes that exist for a collection by using get indexes on the collection. So DB contexts get indexes in our case here. And this gives us some information about the indexes that we do have there. And as you can see, we got 2 indexes on contacts. The first one is actually one on the ID field, and this is a default index MongoDB maintains for you. And then come your own indexes. But you have this default index out of the box for every collection you create, and therefore this is an index that will always be maintained by MongoDB here automatically. And this means that if you are filtering for ID or sorting by ID, which is then the default sort order or the order by which the documents are fetched, you utilize the index for that at least. So now before we have a look at other index types MongoDB supports, let's see how we can configure the index types we already know. And for that, let's again have a look at one person in our contacts data. And let's create our own unique index. The ID index, which you get out of the box for this field, actually is unique by default too. This is a setting MongoDB gives you. And this ensures that you can't add another document with the same value into the same collection. Now, sometimes you have the use case that you also need that behavior for a different field. And therefore you can add your own unique indexes. let's say for email. But of course, we could have also used login UID if we wanted to. But let's use that top level email element here. And let's create an index on contacts with create index, of course. On email, let's say in ascending order. And here, I now pass a second argument to create index where I configure this index. There, I can now set unique to true. If I hit enter, I get an error that we have some duplicate keys as it seems. So this generally worked, but it found a duplicate key here for Abigail Clark. Now let's quickly confirm this by looking into contacts and finding all contacts where the email is this value here, Abigail Clark, without that backslash. If I hit enter, or I simply count that, I see I have 2 persons with that indeed. And this is already one advantage of the unique index. We get such a warning if we want to add it, or if we already had it in place and we tried to add a document with a value that already existed, we would have gotten an error during that insert operation. So unique indexes can help you as a developer ensure data consistency and help you avoid duplicate data for fields that you need to have unique. So the ID underscore ID is unique by default, but you have other use cases like maybe that email here too. And the unique index is a great way for you to not just speed up your find queries, but also to guarantee that you have unique values for that given field in that collection. Another very interesting kind of configuring a filter is setting up a so-called partial filter. Now, in our persons collection, we have persons older than 20, older than 30, and so on. Now, let's say in the application you're building, which is an application for calculating what your friends will get once they retire, you typically only look for persons older than 60. Having an index on the date of birth age field then might make sense. But the problem, of course, is that you have a lot of values in your index that you never actually query for. Now, your index will still be efficient, but it will be unnecessarily big. And of course, the index also eats up size on your disk. Additionally, the bigger the index is, well, the more performance certain queries will take nonetheless. So if you know that certain values will not be looked at or only very, very rarely, and you would be fine using a collection scan if that happens, you can actually create a partial index where you only add the values you're regularly going to look at. So in our case here, contacts, let's see which indexes we have right now, and I only got the ID. So let's now create a new index with create index, of course. And let's create that index on the date of birth age field, but there, still in ascending order, but now with an additional argument here. And that argument for me is a partial filter expression. As a side note, you can also add this to compound index, of course, because now here I will define which field is my interesting field for narrowing down the set of values I want to add. And I will use my DOB age field. Now you could also use a totally different field, by the way. So if you know my queries, which I will run, should only return me persons which have a gender of male, then I could also set this here. And now I would only store the ages of males in my index. So I could set gender male here. And this is a normal query expression for equality. Greater than, lower than is also supported, exists is supported, and you find an article in the last lecture which also mentions which other queries or filters are supported here. So this equal filter is supported, and now what I would create is an index on age, not on gender, but on age, but only for elements where the underlined document is for a male. So this is what I can do. I could have also used the age here though. So I could have also narrowed down my age filter. So this would have been an alternative, for example. Now I still have the other index created, but this would have been an alternative. Not filtering for another field, but for the same field, the age, and then only store elements greater than 60. So whatever you need. Now I got the male case, and therefore we can query for DOB age, let's say greater than 60, and pretty print this, and we'll see something interesting. Here we got a male, but here we have a female. Now, how does this fit our partial index? Well, let's explain our result here. So remove pretty and add dot explain in front of find. What we see here is that a collection scan was performed and not an index scan. Because MongoDB saw that, yes, we were looking for a field that is part of an index, but it also determined that since we say nothing about the gender in our query here, it would be too risky to use the index for that, because the index is a partial index. And MongoDB, as a top priority, ensures that you don't lose any data. So it does not work in a way of naturally filtering out your result sets. Instead, what you have to do to use that index is you also have to filter for the gender here. So if you set gender male here, and I explain that, you see now an index scan was performed with the partial index. You now might be asking, okay, what's the difference between a partial index and a compound index then, if I have to specify both values here? The difference is that for the partial index, the overall index simply is smaller. There really are only the ages of males stored in there. The female keys are not stored in the index. And therefore the index size is smaller, leading to a lower impact on your hard drive. And also your write queries are of course also sped up, because if you insert a new female, that will never have to be added to your index. So this still makes a lot of sense if you often filter for this combination, so for the age and then only males. So then a partial index can make sense. If you rarely look for your other results, if you rarely look for women, this makes a lot of sense. Whenever MongoDB has the impression that your find request would yield more than what's in your index, it will not use that index. But if you typically run queries where you are within your index, your filtered or your partial index, well then MongoDB will take advantage of it, and then you benefit from having a smaller index and having less impact with writes. So again, it depends on the application you're writing and whether you often just need a subset or whether you typically need to be able to query everything, in which case a partial index won't make much sense. One interesting variation or use case of the partial index can be seen in conjunction with a unique index. For this, I will have to create a little demo here, a short example. And I will create a new collection for that. I'll name it users, and there I'll insert many documents, 2 to be precise. The first document is a user with name Max and an email of max@test.com. The second document is a user with name manu and no email, so just that. So I have 2 documents in there, and they don't both have the email field, only Max has it. Now what I can try is I can create the index on users, create index, and let's say I want to index my email field here. So if I index email in ascending order, this works. Nice. Now let's drop that index. Drop index email 1. Because what I now want to do is I want to add this index as a unique index. So unique true, whoops, not here though, but in the second argument to the create index function here, unique true. This also works. But now let me insert some new document. db users, insert 1, and there I'll insert Anna, also without an email. And now I get an error. I get a duplicate key error because that non-existing email for which I have an index is treated as a duplicate key, because now I have a no value, so no value stored twice. So that is an interesting behavior, but some behavior you just have to be aware of. MongoDB treats non-existing values still as values in your index, so as a not there value, you could say, as a null value. And therefore, if you have 2 documents with no value for an indexed field, and that index is unique, you will get this error. Now, if you have that use case and you know, yeah, but I want to be able to turn this into a unique index, and it's okay if some people don't have an email address. If that is what you want to do, then you have to create the index a bit differently. So here I dropped it, and now let me recreate that index, and not just set unique to true, but you can also add a partial filter expression now, and add a filter for the email field, and simply say exists true. So this filter simply says, I only want to add elements into my index where the email field exists. And this will avoid the case of having a clash with unique. If I run this, it works. If I now try to insert Anna without an email, this also works. So now in users, we do have our free users, and only one of them has an email. If I were to try to add Anna with the same email I already have in there, so with max@test.com, then it would fail because this is indexed. All fields where the email exists are indexed. I just used the combination of unique and partial filter expression to not index fields where no value or where the entire field does not exist. And this allows me to still use unique on that field. Now, the last interesting index option I want to show to you is a time to live index. And that's a really cool kind of index that can be very helpful for a lot of applications where you have self-destroying data. Let's say sessions of users where you want to clear their data after some duration or anything like that. Let's create a new sessions collection here. You can, of course, come up with any example you want. And in there, I'll insert one document. And that one document will receive some data, which is some random text. And more importantly, it will get a created at key. And you can name this however you want. It doesn't have to be named created at. Now, this will receive a new date. And it will receive new date like this, which will just be the current timestamp or the current date. So if I look into sessions with find pretty, well then I see this ISO date was created by MongoDB, and this is the current date and time. Now let me add a time to live index here. For that, I'll go to my sessions and create an index, and now I will create that index on the created at field. Now, first of all, you could of course create a normal ascending index here too, and you can order dates just like you can text and numbers. But now I'll get rid of this because I want to add this index a bit differently. Instead of adding it as I did before in ascending order, I will still add it like this, but I will add an additional argument here to configure this index. And there I will add the expire after seconds field. This is a special feature MongoDB offers, and that only works on date indexes or on date fields. On other fields, it will just be ignored. You could add it, but it will be ignored. And there I could say every element should be removed after 10 seconds. Now, if I hit enter here and I look into my collection, you see this value is still there because it was there before the index was added. And the index does not delete elements in hindsight. But if I insert a new element here, you see it's now in the database, but let's now wait for 10 seconds because that is the duration I did specify. And thereafter, you see, actually both were deleted. The reason for that is that adding a new element basically triggered MongoDB to now re-evaluate the entire collection, so also the already existing documents, and see whether this field, which is indexed, fulfills this criteria of only being valid for 10 seconds. And therefore, then it also reconsidered the existing documents. It just doesn't do that right when you add the index, but it does do it whenever you add a new element. So this can be very useful because it allows you to maintain a collection of documents which destroy themselves after a certain time span. And for a lot of applications, this can be useful things like, for example, as I just said, session data for a user of your website, or maybe in an online shop where you want to clear the cart after one day. So whenever you have a use case where data should clean up itself, you don't need to write a complex script for that. You can use a time to live index with that expiry after seconds addition we added in our index. Important to know here, by the way, you can only use that on single field indexes. It does not work on compound indexes, and as I mentioned, it works on date objects. Now we had a detailed look at what indexes do and how you can create your own indexes. And I can only encourage you to play around with that to get a better feeling for your different options and how indexes work. But in order to play around and to understand if an index is worth the effort, you need to know how to diagnose your queries. And I already did show you the explain method for this. The important part here is that you can execute it like this or pass query planner as an argument to get that default minimal output where it simply tells you the winning plan and not much else. Or you use execution stats, what we did a couple of times in this module already, to see detailed summary outputs and see information about the winning plan, a possibly rejected plan, and also some information about how long it took. There also is the all plans execution option, which also shows detailed summaries and which also gives you more information about how the winning plan was chosen. Now we'll have a look at all three of them throughout this module again. For determining whether a query is efficient, it's obviously interesting to look at the milliseconds process time and also compare this to a solution where you don't use an index, so that you'll also have a look whether index scan really beats a collection scan, which it typically does though, but I did already show you some use cases, in cases where you fetch almost everything, where the index scan can be slower. And another important measure is that you compare the number of keys in the index, that is what it means in the output, are examined, how many documents then are examined, and how many documents then are returned. And the keys and documents should be close together, and documents examined and documents returned should be close together, or documents should be 0, so that it looked at 0 documents. And when would this be the case? In a so-called covered query. And now what is a covered query? Well, let me show it to you. For this, I'll create a new collection, customers here, and I'll insert many documents. Now, the first customer has a name, Max, has an age, 29, and a salary of 3,000, let's say. The second document, menu, the age of 30, and a salary of 4,000, let's say. I inserted these two documents. And now let's add an index with create index, of course. Let's create the index on our name here in ascending order, like that. Now if I hit enter, I obviously have that index, and now I can use my customers and explain with execution stats for more information how it would actually find Max. So all customers with the name of Max. Only one in our case here, but of course it could be more. So we see that it of course used an index scan for this because we have an index on the name. We also got no rejected plans right now here. We see that one element was returned and it looked at one key in the index and returned one document. Now, I said that this could even be 0 docs examined. And the question is, when could this be 0? Because we need to get the document in the end. The index only has a pointer to the document, right? Well, the index does not just have the pointer. The index has one value, and that is the, well, indexed value. So Max in this case and menu. So the names are in the index, not just the pointers, but also the values for the indexed field, of course. And you can reach a so-called covered query if you actually would find Max and then also add projection here to not return the ID and only return the name and don't return any other fields. So essentially what I do here is I only want to return the fields which are also the indexed fields, or the indexed field in this case, name. And now you will see that it actually did not examine any documents. It returned 1, but it could do that entirely from inside the index. Now, you will not always be able to reach that state, but if you have some query where you can optimize your index for that to reach that covered query state, as it is called, because the query is fully covered by the index, then you will of course have a very efficient query because you skipped that stage of reaching out to the collection and getting the documents, and that obviously speeds up your query. If you can get this to work, you will have a very fast solution. Now, of course, it does not make sense to build tens of indexes just to cover all possible queries, because then you'll have a problem with writing again and so on. But if you have an opportunity and you have a query that you typically run and you only typically return these 2 fields, it might be worth storing them in a single field, or if it's 2 fields, to store them in a compound index so that you can fully cover the query from inside your index. And this is something very interesting to know, that you can reach that covered query state sometimes at least. Now that we had a look at covered queries, let's also see when MongoDB actually rejects a plan. Now, for that, I'll reuse my customers collection from the last video. And remember, there we have 2 indexes, the standard ID index and our own name index. Now, I'll also add an additional compound index on customers with create index, and I will add age here in ascending order and name. Now, please note that the order here is important for compound indexes. And if I would have put name first, this index here wouldn't make much sense, because then I would have a single field index on name, even though name is the first field in a compound index. And as learned, from left to right, a compound index can be used, well, standalone. So each field can be used standalone from left to right. So in this case, if age comes first, we can also filter just for age and take advantage of this index. For name, we can't take advantage of this index because name is only the second value, is mapped to the respective ages and only sorted within the age category. So if you filtered for just name and you didn't have that index, name could not be supported by index. Here it can, because we have a single field index, and we also get this compound index for the combination of age and name, or just age. So now I create this compound index here, and now I have 3 indexes, of course. Now let's search, or let's explain. So customers explain. Let's search for all persons with a name and an age. So name may be Max and age 30. If I hit enter, you see, the winning plan is an index scan where it used the compound index, and as I mentioned in the compound index lecture, the order in which you specify your arguments when writing the query does not matter. Our compound index was created with age as the first value and name as the second, and in the query I have name as the first value and age as the second, but here in the query the order does not matter. It still is able to use that compound index because we have a simple AND condition here, and you can of course reverse that, and MongoDB does reverse it for us automatically, so to say. Therefore, the winning plan is an index scan using that compound index. Now what we can see is that we now also have a rejected plan. And the rejected plan was to use an index scan just on the name index. That is the single field name index I created. Of course, it made sense for MongoDB to also consider this, because we have that name index, we had a query that included a search for name, so it made sense to consider that name index. But of course, since we have another index which simply fits this query better, this compound index, MongoDB chose to use this one as a winning plan and rejected this one. Now, this is interesting to know. The question, of course, is how exactly does MongoDB figure out which plan is better? For this, MongoDB uses an approach where it simply, first of all, looks for indexes that could help you with the query at hand. So in our last lecture example, we had the name single field index and age and name as a compound index. Since our query, our find method, included a look for name, MongoDB automatically derived that both the name single field index and the age name compound index could be helpful. So it came up with 2 approaches. For other scenarios, you might of course have more approaches. So let's say we have 3 approaches. MongoDB then simply lets those approaches race against each other, but not for the full data set, but it sets a certain winning condition. Right now, that should be 100 documents. So it looks who's the first to find 100 documents. And of course, one of the approaches will be the fastest to reach that threshold. MongoDB will then basically use that approach for the real query. And of course, it would be cumbersome if it would have to do this for every find method, for every query you send to the database, because that obviously costs a little bit of performance. Therefore, MongoDB caches this winning plan for this exact query. So for exactly the query you sent with the fields you were looking for and the values for the fields you were looking for. So it caches this plan as the winner plan for this kind of query. And for future queries that are looking exactly equal, it uses this winning plan. For future queries that look different, that use different values or different keys, it will of course race again and find a winning plan for that type of query. Now, of course, this cache is not there forever. It is cleared after a certain amount of inserts or a DB restart. To be precise, instead of being stored forever, this winning plan is removed from cache after you wrote a certain amount of documents to that collection. Currently, that should be 1,000. So after you added that many documents, MongoDB says, I don't know if the current winning plan will still win because the collection changed a lot, so I should reconsider. The same happens if you rebuild the index. So if you drop it and recreate it, for example. It also gets deleted if you add other indexes, because that new index could be better. So the cache for indexes, or winning plans, I should say, gets cleared when you add new indexes, or when you restart the MongoDB server. Then this also gets reset. So this is how MongoDB derives the winning plan and how it stores it. And it's interesting for you as a developer to regularly check your queries, your find or update or delete queries, and see what MongoDB actually does, if it uses indexes efficiently, if maybe a new index should be added, something you can do on your own if you own the database or you pass that information to your DB administrator, or if you maybe need to adjust the query. Maybe you're always fetching data that you don't really need, and you could get a covered query if you just would project the data you need, which happens to be the data stored in the index. That is why you as a developer need to know how indexes work, because either you need to create them on your own in your next project on which you work alone, or because you can optimize your queries or tell your administrator to optimize the indexes. Now, with that information gained, let's have a look at the last level of verbosity the explain method offers, and that is that we can add all plans execution as a value here. Now what this will do is, it will give us a bunch of output, because here we get detailed statistics for all plans, also the rejected plans. So there we can see in detail how would an index scan on our compound index perform, but then also what would happen if we had that index scan on the name index. How long would that take? How many documents would it there consider? Documents, and how many keys would it consider, how long would it take. Here we have 0 because it's so super fast, but for larger collections you would of course see a difference. And with that you can get detailed analytics on the different indexes and queries and possible ways of running your query, and therefore you should have all the tools you need to optimize your queries and your indexes. Now we had a look at single field and compound indexes and what we can do with them and how we can measure the efficiency. All super important things. Now let me introduce two new types of indexes. And the first one is the so-called multi-key index. For this, I made sure that I dropped my contacts collection, so that huge collection which we imported before. I already did drop it, hence I see false here. And now I will add a new value here. Contacts, insert 1, and that new value, mi, and here I will add hobbies, which happens to be an array of strings. Let's say cooking, sports. I'll also add another array, addresses. Let's say I have multiple ones. This will be an array, and each array is a document there, so embedded documents in an array. There, to keep it short and simple, I'll just have the street, main street, add another document with the street, let's say 2nd Street. Doesn't really matter. If I hit enter here, let's quickly have a look at what I inserted. This is looking good. I got Max, 2 hobbies, which are just strings, and 2 addresses, which are documents. Now let's index an array, because that is possible in MongoDB too. For this, I'll of course create an index again, as we did it before, and this time I will index hobbies. And if you remember, hobbies was an array, right? We see it here, was an array of strings. Let's hit enter, and this works. Now let's try using that. And first of all, let's execute a query where I look for hobbies being equal to sports. And I do find something. I can pretty print that to make it easier to read. I do find Max, of course, because I do have sports in there. Now, the interesting thing is, if I explain this with execution stats, I see that the winning plan was an index scan, and we see that there is multi-key is set to true for my hobbies index. MongoDB treats this as a multi-key index because it is an index on an array of values. And technically, multi-key indexes are working like normal indexes, but they are stored a bit differently. What MongoDB does is it pulls out all the values in your index key, so in hobbies in my case here. So it pulls out all the values in the array I stored in there and stores them as separate elements in an index. This of course means that multi-key indexes for a lot of documents are bigger than single field indexes, because if every document has an array with, let's say, 4 values on average, and you have 1,000 documents, and that array field is what you index, you would store 4,000 elements, because 4 times 1,000. So this is something to keep in mind. Multi-key indexes are possible, but typically are also bigger. Doesn't mean you shouldn't use them. If you typically query for an array and the value in an array, well, then it makes sense to turn this array into a multi-key index. That is perfectly fine. So now we learned that we can use a multi-key index, and we are using one on hobbies. Now let's also add one on addresses. Contacts, create index, and there I'll index addresses 1. Now this also worked. It created that index. And now let's try to utilize that. Let's reach out to contacts and let's explain what's happening with execution stats so that we can see if that index gets used. And let's find all addresses where the street is Main Street. If I hit enter here, we see it actually used a collection scan and not our index. The reason for that is that our index, of course, holds the whole documents and not the fields of the documents. So MongoDB does not go so far to pull out the elements of an array and then pull out all field values of a nested document that array might hold. So our index would only get used if I were not looking for the street in the addresses I have in that array, but if I were looking for addresses holding some document. So if I were looking for addresses where street is Main Street, if I were looking for that, you see it would have used an index scan because it is the whole document which is in our index in the end. MongoDB pulls out the elements of the array. For addresses, a single element in the array happens to be a document, so that document is what MongoDB pulled out and what MongoDB then stored in the index registry. And therefore, this is something to be aware. What you can do, though, is you can create an index on addresses.street. This also will be a multi-key index. As you can see, if I now repeat my earlier query where I was looking for addresses street, if I repeat that query now you see it uses an index scan for this, and it is a multi-key index. So you can also use an index on a field in an embedded document which is part of an array with that multi-key feature. You should just be aware that, of course, using multi-key features on a single collection will quickly lead to some performance issues with writes, because for every new document you add, all these multi-key indexes have to be updated. And if you add a new document with 10 values in that array, which you happen to store in a multi-key index, then these 10 new entries need to be added to the index registry. And if you then have 4 or 5 of these multi-key indexes per document, well, then you quickly are in a low performance world. Still, multi-key indexes super helpful if you have queries that regularly target array values or even nested values or values in an embedded document in arrays. There are a couple of restrictions, or one important restriction to be precise, when using multi-key indexes, and that is that if you add index, a multi-key index, and you add it as part of a compound index, that is generally possible. I can add name in ascending order, and name is not an array, it's just a single field. And I can then add hobbies like this. This works. However, what won't work is that I say I want to have a compound index made up of 2 or more multi-key indexes. So addresses 1 and hobbies 1 will not work, because you can't index parallel arrays. The reason for that is simple. MongoDB would have to store the Cartesian product of the values of both indexes, of both arrays. So it would have to pull out all the addresses, and for every address, it would have to store all the hobbies. So if you have 2 addresses and 5 hobbies, you already have to store 10 values. And that, of course, becomes even worse the more values you have in addresses. So that is why this is not possible. Compound indexes with multi-key indexes are possible, as you see here, but only with one multi-key index, so with one array, not with multiple arrays. You can have multiple multi-key indexes, as you can see here, in separate indexes, but in one and the same index, only one array can be included. Speaking of multi-key indexes, there is a special kind of multi-key index, a text index. Let's say we have this text stored in a field in our document. Could be the product description of a product. Now, if we want to search that text, we saw before that we can use the regex operator, and that is, however, not a really great way of searching text. It offers a very low performance. Better is to use a text index. And a text index is a special kind of index supported by MongoDB, which will essentially turn this text into an array of single words, and it will store it as such. So it stores it essentially as if you had an array of these single words. One extra thing it does for you is it removes all the stop words and it stems all words, so that you have an array of keywords essentially, and things like is or the or a are not stored there, because that is typically something you don't search for because it's all over the place. The keywords are what matter for text searches typically. So this is the text index. Now let's have a look at such a text index, and for that I'll, insert many products into a newly created products collection here. So the first product will have a name, or let's say a title to mix it up, title, a book, and it will have a description. This is an awesome book about a young artist. The second document I add here should also describe a product, will have a title of red t-shirt, and there we'll have a description of this t-shirt is red and it's pretty awesome. So after finding that missing quotation mark, it now worked fine for me. And now if I have a look at my products and I print this, here are my 2 products. Now let's use a text index. Let's use it on the description field, let's say. So first of all, output our products again so that we can see them. And now we can create a new text index, again with create index, as we create all indexes. And I say I want to create it on description. And now it's important. Don't add 1 or -1. You could do this, but then it would simply index this as a single field. index, and you could then search for exactly this text to utilize the index, but not for individual keywords. You need the text index so that MongoDB splits this up. So using this will not work. So let's quickly drop that index like this. And let's recreate the index, but now not with a 1, but with the special text keyword, text in quotation marks. This will create a text index, which is a special kind of index where MongoDB will go ahead and, as I mentioned, remove all the stop words and store all the keywords in an array essentially. So let's have a look at this. This is the data we have in there in general. And now let's use products and find. And here, let's now use the special $text key and search. And for that, you pass a document as a value for $text, and there you need $search. Now you might be wondering, why do I not need to specify the field in which I want to search? Why don't I have to add description? Instead, we just add, hey, I want to search for some text. The reason for that is that you may only have one text index per collection. Because text indexes are pretty expensive, as you can imagine, if you have a lot of long text that has to be split up, you don't want to do this like 10 times per collection. And therefore, you only have one text index where this could look into. You can actually merge multiple fields into one text index, as I will show you in a second, and you will then look through all of them automatically. But you can only do it like this. You can't say, hey, I want to search for text in description like this. This won't work. So now for search, we simply enter the words we want to look for, like awesome. And the casing is not important here, by the way. Everything is stored as lowercase. If I hit enter, and I pretty print this, you see I find both products, because in both products we have the term awesome. Now let's repeat this, but let's now just search for the term book. So here, I'll search for book. And now you see I only get, well, this text or this document where we have book in the text. Now what if I search for red book? I have red in the other document. Well, then I find both again, because this is now actually not treated as one connected phrase where it would look for a red book, but it simply looks for documents that have a red text or some red in a text, and for documents that have book in a text. Of course, you can also search for a specific phrase though. You can search for phrases by wrapping that phrase in double quotes. And since we are in double quotes already, we have to escape them with a backslash double quote. We have this at the beginning and at the end of the phrase. And now we don't find anything because we have no red book phrase anywhere in our text. For example, awesome book would work though. So if I look for the awesome book phrase, we would find this document because we have awesome book right there. Now this is really powerful and much faster than regular expressions. So this is definitely the way to go if you need to look for keywords in text. Now let's do a different query. We still have that text index on the description, and let's search for awesome t-shirt. If I do this, I find both entries because I have awesome here too in the first product. Now finding both might be fine, but you typically would want to order this differently. For us humans, it's pretty clear that the second product is the better hit because there we have both awesome and t-shirt. So it would be nice if that would come first in our result list. And we can actually get there. Because MongoDB does something interesting or special when managing such a text index or when searching for text in a text index. We can find out how it scores its results. And let's first of all find out with the help of projection. So here I'll add a second argument to my find method to project the results. And I will simply output a score field here where I can use a special meta operator to add text score. This is a meta field added or managed by MongoDB for text searches here with the $text operator on a text index. If I do this, you see the score MongoDB assigned to a result. And here, it even automatically sorted by that score now, as you can tell. So here we see that the score is much higher for t-shirt and awesome than for just awesome. and it automatically sorted for us here. But if we wanted to make sure, we can of course also add sort here, and we can then sort by score, where score is a document with $meta and then text score written like this as a text. And I should add a dot in front of pretty. And now it's definitely sorted. It was before, but now we enforce sorting by looking at that meta text score, which MongoDB manages for us. So this is simply a construct you can remember for when working with text and text indexes. You can extract this meta information text score, and both these words have to be written like this, from MongoDB, so to say. It manages that for us, and we can see how it scores the results. And as you can see, we can then use that to order too. Now, I did mention that you can only have one text index per collection. And that is true. If we get the indexes for products, we see we have one text index down there. And you see it assumed the default language of English. We can change that, by the way. I'll come back to that. But for now, let's simply try to add another text index. Because in products, if we find one, the title is of course also text. So we could say products create index, and then say title should also be a text index like this. Now what we get here is essentially an error, index options conflict. Now this is a bit hard to read, but in the end it tried to create the index which we already have, because you can only have one text index. What we can do though is we can merge the text of multiple fields together into one text index. For this, I first of all need to drop my existing text index. And now dropping text index is a bit harder. You can't do title text. This doesn't work, as you can see. But what you can do is you can drop it by the name, by the index name. So you can copy that index name you have up there with get indexes, and then you can simply drop it by the name. We did drop by name earlier in this module too. Whoops, needs to be in quotation marks though. So now this is gone. Now this old text index is gone. And if I repeat get indexes, we see we only have the default ID index now. And now we can create a text index again, but now we can actually merge together multiple fields by simply adding them like this, description text. Now there still will only be one text index, but it will contain the keywords of both the title and the description field. So if I hit enter, this works. And now I can of course also search for items we have in the title. So if I find one, you see, for example, I could search for book because I also have that here. Now we won't see a difference because we had book there before, but now it will search for both. And I can prove this by simply inserting a new product with a title of a ship and a description of floats perfectly. And as you see, we have ship only in the title, not in description. So now with that added, we can of course reach our products and find, with the help of $text, for a search term of ship. And again, the casing doesn't matter here. And I do find one document because ship is in the title, and I now have a combined text index. With text indexes, you can also not just search for words, but you can also rule out words. Let me show you what I mean. If I would search for awesome, and I pretty print that, we find both the book and the t-shirt. Now let's say I only want to find awesome products which are not t-shirts. So I could do this by adding awesome and then minus t-shirt. If I do this, I only find the book, because the minus in front of a word means that this word should be excluded. And this is really helpful, of course, because it allows you to run narrowed down queries like this one, where you only find awesome products which are not t-shirts, or which at least don't have t-shirt in the title or in the description. Now we're almost done with text indexes. Now I want to drop my index again, because now I want to show even more interesting things you can set up when adding the index. So for that, first of all, I need to get the name by getting all indexes. This is now the name of my text index. And now I can drop it by that name by running db products, drop index, and then adding that name here. Now the index is gone. And I did drop it because I now want to create a new index. With products, create index, a new text index, of course. There, I want to include my title as a text index and my description as a text index. But now I'll pass some config here, because there are two interesting things I can configure about text indexes. The first one is the default language. I can manually assign default language here to a new value. You saw earlier that the default language it assumed was English. And if that is the case, well, you can of course leave that. But you could also set this to a different language here. And I could add German here. Now, you're not free to enter whatever you want here. There is a list of supported languages, and in the last lecture you find a link to those languages. Now, the field here is not just some cosmetics. We can later use it when searching for text, but most importantly, what it will do here is it will define how words are stemmed, so how prefixes and so on are removed, and it will also define what stop words are removed. So words like is or a are removed in English. In German, it would be ist and der. So the language here is something you should specify when you know which kind of language or which language will be stored in your text. And you should pretty much know that for any application you're building. Now I'll set it back to English here, which is my default, and I wouldn't need to specify it here, but I'll set it here explicitly to make it clear that you can set the default language and that this will affect which words end up in your index. Now another cool value you can set here is that you can define different weightings for the different fields you're merging together. So here I'm merging together title and description. Now, maybe I want to merge them, but I want to say, yeah, the description should be a higher weight. And the weights will become important when MongoDB calculates the score of the result. Because you might have awesome in the title, but that should not count as much as in the description. And to set up such weights, we can add a weights key here in the config object in the document we pass as a second argument to create index. And there, weights itself holds a document as a value. And in this document, you can now reference your field names, like title, and simply assign weights that are relative to each other. So we could have title 1, description 10. And now description would be worth 10 times as much as title, or would weigh in 10 times as much. So if I hit enter, we now have this text index created. If I now find all products in my collection here, you see it looks like this. And now let's again search with a text index. So I will use my products to find with $text. And now there, we saw the search keyword already. Now, besides the search keyword, which I'll fill out in a second, you can also specify the language, German here. This is more interesting if you use a different way of storing the language, because you can even have different languages for different documents. That is an approach which I'll highlight in the last lecture of this module. You'll find an article there to this advanced setup. Interesting for us here also is that you can also turn on case sensitivity with case sensitive set to true. Now the default is false. With true, you could suddenly search in a case sensitive way. So that's just another side note. But let's go back to just the text and let's search for red. Now obviously this works. Let's now also add the score here with $meta text score. And let me also add pretty to make it easier to read. And you might not remember the exact number we had earlier, but it was not 6.6666. It was a different number earlier. And this is because we now added some weights. And I can prove this if I simply drop my index. So first of all, I get my indexes to get the name. Here it is. Then I quickly drop the index here, like this. And then I re-add the index with create index, but now without assigning weights. So I will remove that weights assignment here at the end. I only set the default language, which I also could omit, but doesn't matter. So now we have a text index working in the same way as the other one, but without weights. And now if I execute that same find query, you see the score is a different one. It's not 6.6666, but 1.266, because the score is now calculated differently because weights don't play a role. And weights can of course help you, well, put the weight on the field that holds your most important keywords. This is the text index. As I mentioned, you'll find some further articles in the last lecture of this module, but the vast majority of important features were covered here. And managing the text index might not be your primary task. Being able to use it with things like the meta score and understanding how it works, that it might search across multiple fields, is definitely something you need to know, and hopefully something which became clearer here. We're almost done with this module. One last word about how you build indexes. And with this I really mean how you add them. You can add them in two ways, in the foreground and in the background. Thus far in the module, we always added indexes in the foreground with create index, just as we executed it. Now, actually, something we didn't notice because it always happened instantly, basically, actually during the creation, the collection will be locked and you can't edit it. On the other hand, you can also add indexes in the background and the collection will still be accessible. The advantage of the foreground mode is that it's faster, the background is slower. But if you have a collection that is used in production, you probably don't want to lock it just because you're adding an index. So let me show you how you can add an index in the background and which difference that makes. To show the difference that this makes, I prepared a JavaScript file which you find attached to this video. The shell can also execute such files by simply typing Mongo and then the file name. creditrating.js is the file. Now what this will do is that Mongo still connects to the server, and then it will execute the file and basically execute the commands in there against the server. And in that file, I essentially have a loop that will add 1 million documents to a collection with random numbers in there. Now executing this will take quite a while, can take multiple minutes depending on your system. You can always quit it with Ctrl+C, and you can also, of course, edit the code to reduce the number of documents that are created. Now, I will leave that running and I will be back once it is finished. Again, don't worry if it takes a while, that is totally normal. So this completed successfully for me. I can now connect with the Mongo command. And on the server, let's run showdbs, and it's the credit database that was added now. So let's use credit. And in there, if you show the collections, you should have a ratings collection. And if you count that, you should see that there are 1 million documents in there. Now, nothing in there is indexed. And before we start adding an index in the back or foreground, we can take this as an opportunity to practice indexing a bit more. So let's have a look at ratings and find one element only. This is how a single element looks like. We get an age in there, we get a score for the person. And let's now say we wanna, for example, index age. So we can create an index on age in an ascending order. And you already see this now doesn't finish instantly. Really quick still, but not instantly, because we have 1 million documents which have to be indexed. And now let's use that index. For that, I'll use my ratings. And I will also explain the results with execution stats. And now let's find all ages where people, let's say, are older than 80. Now, here you see close to 100,000 keys were examined because this is totally randomly generated. And we used the index scan here, where we had to look at all these keys, all the docs, and return these docs. Took 200 milliseconds. Now let's drop that index. With db ratings, drop index, and we had an index on the age in ascending order, so let's drop that. And let's repeat this query. And there we can already see this took longer, like 400 milliseconds, so double as long. So the index did already pay off there. But of course, this is already something you know. Now I wanted to show you that the index creation takes time. Now remember, I just deleted my index, right? So I only have the default index on there right now. So now I will actually create an index and I will show you that this will block us from doing anything with this collection. For that, I will open a new tab in which I also connect to my Mongo shell, and I will already prepare a query there. So now I'm connected to the same database, and there I will prepare ratings find 1. Now I need to switch quickly later because it doesn't take that long, but I'll try to execute this whilst the index is getting created. So now I will create that index on the age again. So I hit enter, and you see, this doesn't finish here. It takes a while. It only finishes after this creation is finished, essentially. If I drop that index and I'm prepared to create it again, and here I try to insert one document with, let's say, person ID, some random text, which of course is not in line with the other IDs, which are numbers, but doesn't matter, some score, and an age of, let's say, 90. So I prepared this. I want to insert that person. And I again create that index and try this. It doesn't finish. It only finishes after the index creation is done. So after the collection is unlocked again. So it's not getting an error here. It is working in the end. But whilst the index is getting created, it's not working. It's basically deferred until the index is created. Now, our index creation here is still going fairly fast. Didn't take much longer than a second, probably. But it's not hard to imagine that for more complex indexes, like a text index, let's say, or for even more documents and more complex documents, that index creation will easily take longer. But especially more complex things like text indexes will take much longer. And then this will be a problem, because then the database or the collection might be locked for a couple of minutes even. So this is not an alternative for a production database. You can't suddenly lock down your entire database and your application is not able to interact with it anymore. And that is why you can create it in the background. So let me again prepare this insertion command here. And let me go back and first of all drop the index, and then prepare the creation again, but now with a second argument where we previously set things like the default language. Now I will set background to true. The default is false, which means it's created in the foreground. But if you set this to true, it will be created differently in a way where the collection doesn't need to be locked. So now if I do this and I hit enter here and I hit enter here, you see it's inserted immediately, even though the index creation still blocks this thread. We couldn't enter any other arguments, but technically it happened in the background without locking the collection. So this is a very useful feature for production databases. You don't want to add an index in the foreground there, especially not if it will take quite a while. That's it for this module. We had a very detailed look at indexes. Indexes allow us to retrieve our data more efficiently. Mostly we saw some exceptions in this module, but generally they speed up our queries and also the sorting. We can use single field, compound, multi-key, and text indexes. Now there are a couple of other indexes, and for example geospatial indexes are something we'll see in the geospatial module, but these are the most important indexes for now. And it's also important to understand that indexes don't come for free. They will slow down your writes. That is something you always have, but this still often is worth the effort. But this is something you should keep in mind because it means that you should not create an index for every single field. This will be inefficient because all these indexes need to be updated with every insert, update, or delete. We can use indexes for querying and sorting, and compound indexes have this special behavior where you can use them left to right. If you have a compound index made up of name and age, you can either use that index to optimize your queries where you look for name and age with some criteria, or also for queries that just use the name. Just the age is not possible due to the way this is stored. To find out whether your queries and indexes do their job in a good way, you can diagnose your queries with the explain method. Also remember the options you could pass to explain: query planner, execution stats, and all plans execution. The output there gives you a detailed look into what MongoDB did and how it derived this plan it used. And it also gives you an idea of how you might optimize your indexes. For example, if you have a large gap between the keys it had to look at and the documents it actually retrieved. When creating your indexes, you can also configure them. For example, you can add a time to live if the index is placed on a date time, or you can turn them into unique or partial indexes. For text indexes, you can also assign weights and a default language. Now, this is what we covered in this module, and this hopefully helps you create efficient databases with efficient indexes and then writing efficient queries for that.